Weird technology stuff. All right, so we're dealing with surface area, and we're dealing with very symmetric surfaces, surfaces that are created by rotating a curve around an axis. So that's the only type of surface we can find the surface area of right now. When you get into Calc 3, you'll figure out general ways to find surface area for weird surfaces. For us, our surfaces are very, very symmetric, very nice. So recall that our generic formula for surface area is this. And the way I like to think of it is that we're doing circumference, 2 pi r circumference. So if we imagine a point on our curve and we imagine it rotating all the way around, that's our circumference, 2 pi r. But then we multiply it by a little diagonal distance. And that's what ds is. ds is a tiny diagonal distance. Like dx is a tiny horizontal distance, dy is a tiny vertical distance, ds is a tiny diagonal distance. But once again, we don't know anything about s, so we need to convert the s over to x or y. So we can convert ds into either dx or dy. And that's the arc length expression that we've used a lot with the big square root. So what we talked about last week was that if we rotate around the y-axis, we are thinking about using a dy, and this radial distance is horizontal, so we need to present our function as an x value. We need to isolate x. Oh, that's done already, so that's good. That's already done for us. To get to our ds, we are going to have to take x and find its derivative. So let's go ahead and do that first. So to build up ds, we need to do the square root of 1 plus x prime squared. So let's go ahead and take the derivative. So x prime will be 1/2, and then the base stays the same. We subtract 1 from the exponent. So that's the power rule part of the derivative. Then we have the chain rule part of the derivative. We brought the power down, we left the base alone, we subtracted 1. Now we want to multiply by the chain rule part, which is the derivative of the base, 12 minus 2y. So there's our derivative expression. We can simplify it a little bit. Let's write it as 6 minus y, dividing the 2 into the numerator, and then we'll put that square root in the denominator since we have a negative 1/2 as the exponent. So there's x prime. Now we know that our ds, we have square root of 1 plus, in this case, x prime squared times dy. So we're building up that radicand. So now we're going to square that x prime and then add 1 to it. So we're almost there. Let's go ahead and square it. So x prime squared will be 6 minus y squared over 12y minus y squared. There's x prime squared. Okay, ugly. So now we have our ds. Let's go ahead and set up our integral for our surface area. So once again, 2 pi r ds. So let's come over here. So the 2 pi can come to the front for sure. And then r. R, horizontal distance, is just the function that was given to us. It was already in horizontal form. So that root is just going to drop right in here, 12y minus y squared. So there's our 2 pi r. ds, square root of 1 plus x prime squared. There's our x prime squared. We'll put a 1 right here. So 1 plus 6 minus y quantity squared divided by 12y minus y squared. and then that has a dy differential. I'm going to make that square root, make sure it's obvious that everything is in that square root. Right, that square root covers all of that stuff. All right, limits of integration. Since we have a dy, we're looking on the y-axis for little y values. And those y values are coming from, let's see, they gave us the interval, 2 to 10. So those will be our limits of integration from 2 up to 10. And there's our surface area integral. That's technically the hard part. So is there any piece of that you're not sure about? Usually it's the setup that you get tangled up on.
You missed a y in the denominator of the...
Yes, that's a 12y minus y squared. Yes, thank you. Right in there, 12y. Thank you, good catch. We would notice real soon when we couldn't simplify those square roots. Be like, uh-oh. All right, so now we combine our two roots. So back to algebra. And the algebra tells us that we take the inside of this root here and we distribute it to the inside of the other root. So we have to multiply it across. So we're going to take, imagine that whole clump, multiply it by 1, which gives us itself. So that's going to be a 12y minus y squared. And then we take that whole clump and multiply it by the second fraction, and we notice that it matches the denominator perfectly, so it will cancel with that denominator, leaving us just the numerator. So that'll give us, we'll FOIL this out in 1 second. So there is our simplification. And at this moment, we still have our fingers crossed, because if we have a square root with a square in it, we're not going to be able to integrate that. Because there's no linear function on the outside that is a multiple of the derivative. So we're hoping all the squares cancel. Because if we have a square inside that square root, we're going to be stuck for now. 12y minus y squared. FOIL this out, we're going to get plus y squared minus 12y, oh, everything's canceled in. Minus 12y plus 36. dy. All right. So all that stuff cancels. The y squareds, the 12y's. Square root of 36 is 6. That can clearly pop to the front. Constants love to be in front. They're like dogs. So that goes all the way to the front. So we have a 12 pi out in front. And you may see it already, but let's just write it out. This integral then is from 2 to 10 of dy. And what is the integral of dy from 2 to 10?
10 minus 2.
10 minus 2, so we get 8, right? So anytime we integrate a differential, we get the length of the interval. So it's going to be 8 times 12, which is 96, multiplied by pi, and that will be our surface area. So surface areas are sometimes a little nicer than just arc length, because you end up with things that can combine. Arc length just has the square root, so unless it's really nice.
I just get a 12 pi? The 6 and the 2.
So the 6 and the 2, yes. So this 6, the 6 is coming from the square root of 36, which will then jump to the front. All right, one more surface area one. We'll do this manufactured application. Basically, we want to find the surface area. And it says how much paint do we want if we're going to paint this surface with 1.5 millimeters of paint. So once we find the surface area, multiply by the thickness, and that will tell us the volume of paint. The only rub here is we've got to be cautious with our units. This is given to us as millimeters, and
That's for meters.
yeah, it's meters, and I'm not even seeing the word oh, there it is, thank you, yeah. I knew it was in there somewhere. So we just need to convert the millimeters to meters, move the decimal, a few places to the left, divide by 1,000. Okay, so surface area though, there's the math part for us. We've got this portion of we're going to create a portion of a sphere. It's going to be like a napkin ring-ish thing. So we're going to take this circle from -8 to 8, and we're going to take just the upper portion of that circle. So just that arc up there, rotate it around the x-axis. That's going to create a surface. The radius of if we take a point on this curve, rotate it around to create our circumference, the 2 pi r, that radius is vertical, so we want to make sure our surface is written as a y value to measure vertical distances. So we want to take the equation of this circle, isolate y, and choose the positive value. Positive y would give us this, negative y would give us down here. So we're choosing to take this equation, isolate y, and choose the positive square root to get the top. So there's our function. And that function is representing r. That's the distance to the axis of rotation. So once again, we know that surface area come on. So you're going to make me go back up there and click that again. Okay. So we know surface area is 2 pi r ds, so we're going to pull out the 2 pi. And the r, again, is just the function. So that's going to be root 100 minus y squared. So there's the radius, that's the distance to the axis of rotation. Now we need the ds. The ds is that square root of 1 plus x prime squared. So we have to find x prime, and then, or in this case y prime, and square it. The derivative squared. So let's come down here, find our derivative. So y prime will be 1/2 base to the negative 1/2. So once again, that's the power rule part of the derivative. Exponent comes down, the base stays the same, we subtract 1 from the exponent, and then the chain rule piece of the derivative, we take the derivative of the base, put it in there. The 2's will cancel, so that 2 and that 2 will cancel. And we know that we need to build this up to a y prime squared, and then add a 1. So let's go ahead and do the y prime squared outside of the square root, just because it's cleaner. Okay, the 2's have canceled. The numerator is negative x, and if we square that, we get positive x squared. This root is in the denominator, and when we square a root, the root goes away. So we'll have 100 minus x squared in the bottom. So that's our y prime squared. So let's drop that into this square root up here. We're going to add 1 to it and drop it in. So it's going to be 1 plus x squared divided by 100 minus x squared. Why do I have 2 different letters here? What's going on?
You wrote y instead of x.
So I miscopied that, right? That should be an x squared inside that integral. Right, so that right there is just a typo. So that goes away, and it should be an x. Okay. Must be vigilant, always paying attention. If something doesn't seem right, double check. And a dx on the outside. There we go. And then our limits of integration, we are integrating with respect to x, so we're integrating throughout an interval on the x-axis. we have two choices. We could go -8 to +8. We could go 0 to 8 and double it. I mean, I guess we have another choice. We could go -8 to 0 and double it too. But whatever we want. We have so much freedom here. Let's do 0 to 8, and then we're going to double it. So let me put a symmetry 2 just out in front here. So let's put a 2 right there. So that 2 is symmetry. So we're going to take this portion of the curve going from 0 to 8. There's our interval right there, and rotate that around.
Is there a reason why you chose 0 to 8?
It's nice to have 0 and a limit as a limit of integration, and it makes most common sense is to integrate this direction. You could go -8 to 0 though, or -8 to 8.
Right.
0 just tends to make a clean solve when you're
Because
pointing
you
at
can't
0
use
into
it.
1.
When you substitute 0 in, it's a little easier than substituting -8 in. Anytime we substitute a negative number into an antiderivative, there's potential for something to go wrong. So if you can use symmetry and get a 0 as a limit, usually we'll do it. Definitely don't have to though. And you can try it both ways and just see how it all plays out. So we'll end up with a 4 pi out in front. We're going 0 to 8. We have a root and a root, so we have to combine them. So once again, we think of this glob in this first integral, in this first radicand, that thing, it's going to distribute to each of the terms in the second square root. So that's got to go to the 1, and it's got to go to the whole fraction. So share it across. So we will end up 2 square roots become 1. 100 minus x squared times 1 is 100 minus x squared. 100 minus x squared times this fraction, yeah, those cancel. So we get just plus x squared. So once again, the square roots combine really nicely. The x squareds are going to cancel. We end up with root of 100, which is 10. That comes to the front, makes the 40. And then 0 to 8 dx. And 0 to 8 dx?
8.
8. Yep, length of the interval. Length of the interval. So we're going to end up with 8 times 40, which is 320 times pi. So this is the surface area. And then if we want the volume of paint, the volume of paint would be 320 pi. That's the area of the surface. We want to multiply by the thickness of the paint, so multiply by 0.0015. Whatever that gives you.
0.48 pi.
0.48 times pi, and this would be meters cubed. So that's how much paint we have. Make sense? So a lot of this stuff, especially in this chapter, super visual, and it's boiling down to really common sense types of things: vertical distances, horizontal distances, symmetry. And when you envision that point rotating around your axis, you're thinking of a circle. And then when you multiply by ds, you're thinking of multiplying by a tiny diagonal line, which creates the frustum of a cone. And so you essentially are thinking of all these little frustums being added together to get the total area.
Now, if we were to just actually do 0.48 times pi,
Yep.
leave that as our answer, would we be?
So it's all going to depend on what the question says. If it says leave pi in, we'd leave it in. If it says approximate to 4 decimals or 2 decimals, then we would multiply the two together.
And it says exact.
So if it says exact, you leave the pi in. Yep. Which you always assume. Unless it says approximate, you always assume you leave root 2, you leave pi, you leave all those irrational numbers as symbols.
And those Lambert functions.
Are there more rationals or irrationals?
Irrational.
Yes. Many, many more irrationals. Many more irrationals than rationals.
Because rationals is poke holes, all the irrationals is everything.
Yeah, so so if you get into higher level math classes, you start talking about the density of subsets. So you can talk about the density of the rationals within the real numbers or the density of the irrationals within the real numbers. But it turns out there are many, 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 many more irrationals, which is slightly counterintuitive because most of the time we deal with rational numbers and, it just sort of feels like they're more common.
Or are we biased?
Yes, exactly. That is our human bias because rationals are easier to deal with than irrationals. But if you just grab a number off the number line, 99% of the time it would be irrational. There's many, many more irrationals than rationals. Okay, so let's go to our section on physical applications. So, physical applications, the first thing we're going to do is deal with is mass. And mass is defined to be density times volume if you're dealing with a three-dimensional object, if you're dealing with a solid, and there's uniform density. Now, most of us probably think about this more like density is equal to mass per unit volume. That's kind of the more intuitive way. It's the way I think of it. Usually if someone says density, I think, oh yeah, mass per unit volume. How much mass is there per little chunk of the solid? But generally, we'll want to rewrite it like this. Mass is density times volume because usually we're trying to find mass. So that's how the formula will tend to look for us, even though if in your mind, if you think of it that way, then just multiply by volume. Now, this is for a three-dimensional solid object. So three-dimensional density. You can also have two-dimensional density and one-dimensional density. So if you have a really thin plate, which mathematically we call it a lamina, a very, very, very thin plate, so essentially the thickness of it is negligible, then you can talk about two-dimensional density. So you could have mass per, instead of volume, mass per unit area. Or if you have a very thin wire, you can have one-dimensional density. So a rope or a wire, a string, they'll talk about mass per unit length instead of volume. So we have to be a little bit aware, because sometimes they don't really come out and tell you that we're dealing with one-dimensional density. You just have to sort of look at the units and say, oh gosh, the density they gave us is per length, or per, we won't see per area in here, but in Calc 3 you'll see per area. So you'll see 2D density in Calc 3. For us, it's either going to be mass per volume or mass per length. Yeah?
What does 2D density look like?
Like a thin metal sheet. Like very thin metal plate is what you usually visualize.
Is it like the formulas?
Say again?
Like the formula?
Oh, so just say area instead of volume.
Oh,
That's awesome.
So it'd say area instead of volume or length instead of volume.
okay.
So, for example, here, one-dimensional object. So if we imagine a super thin wire, a thin bar, tiny bar, so this is one-dimensional density, so there's a dx here. So first off, the density is not always uniform. Sometimes it's variable. And anytime the density is variable, to find the mass, you have to integrate. You can't just multiply. And this formula, the simple formula, only works if you have uniform density. So if the density is variable, which is what rho represents, so rho, Greek letter R for density, I forget why. So this is representing a variable density. Now, if our object was a solid, we would end up finding the mass with a triple integral, and there'd be 3 differentials here. If we were doing a solid object, which is what you'll do in Calc 3. You get to do that in the summer or the fall. Hopefully the fall, because the summer Calc 3, 10 weeks, and it's only online. Not my recommendation. So we are dealing with a wire here. So this is one-dimensional density, so we have a one-dimensional differential. dx is a little piece of horizontal distance, little piece of length. So here we have density times length, and that gives us mass. So in here, we can think of this as a tiny piece of mass, and then we integrate from A to B, add up all the little masses to get the total mass. Riemann sum. Limit of a Riemann sum gives us that definite integral. So this is sort of the simplest of all possibilities. We're just trying to find the mass of a wire. Here we have two problems where we have variable density. So the mass is calculated by integrating over the interval, and we integrate our variable density, and that's it. That gives us mass. Mass is integral of density.
Cubed, not squared.
Cube not squared. Thank you. Cube not squared. And so nothing complex here. This won't be on the exam. This is our mass, whatever units they give us, if they give us units. Of course, this is math, so a lot of times you just forget the units.
Right,
So-
6.7 in its entirety won't be on the test.
No. 6.7 will heavily be on the test, just not this slide.
Oh, okay.
Something as easy as
Yeah,
one.
we're just sort of getting into the concept that integrating density is mass. Yeah, there'll be a lot of 6, 7 on it for sure. All right, so then this one, same idea. We're just going to integrate the density to get the mass. We're going to integrate on 0 to 4. Reverse chain rule. The integral of an exponential is itself. Anytime we're differentiating or integrating an exponential, it's itself. If you're differentiating, you multiply by the derivative of the exponent. If you're integrating, you divide by the derivative of the exponent. So there is our antiderivative from 0 to 4. So we'll have -5/2. Pull the constant to the front. And so then we're just thinking about this exponential piece right here. If we pull that constant to the front, we just have that. Plug in the 4, plug in the 0, take the difference. Don't be lulled into thinking plugging in 0 gives 0. It's very easy to goof that up. So e to the -8 minus e to the 0, that's -1. So that will be our mass, kilograms, grams, whatever. That's the mass. If you want to, you could distribute the minus. If you are just sort of thinking mentally in your head that, well, gosh, this is mass, it better be positive. So maybe we'll write it that way to emphasize that that's a positive number. Doesn't matter, though. And if they ask you to approximate, you just type it into your calculator and get it. Everybody agree that's positive? E to the -8's very tiny. Subtracting tiny from 1 is still positive. So that's the concept of mass. Integrate density to get mass. Most of the objects we deal with are going to have variable density. So if you want to build up to mass, you've got to integrate that density function. All right, so here's where we start to get into slightly more complicated options. So work. Simplest case of work. When you're in physics, many of you have probably already seen the spring problem. It's the simplest type of work problem. And it's because for a spring, that's on the next slide. For a spring, the force is linear. For a spring, the force is determined by Hooke's law. Force is going to be kx. It's just going to be a linear function. Super easy. In general, we think of work as force times distance. And again, if the force is constant, if you're applying a constant force, then you can just multiply by the distance traveled. Like if you have a book and you just lift it straight up, you multiply the distance that you lift the book, multiplied by the force that you're applying to the book to lift it. So in that simplest case is just lifting a block, lifting something that you apply a constant force to, pushing something, constant force. Most of the time, we're going to be dealing with a variable force. Like you imagine a spring, as you compress a spring or stretch a spring, the first inch is a lot easier than the second inch, which is a lot easier than the third inch, right? That force is not constant. right? So it's got a variable force in order to compress or to stretch a spring. So most of the time, that's going to be a variable function. Excuse me. Almost better. Now, if we want to find the work, the idea with the Riemann sum is that you subdivide, you imagine a bunch of little intervals. On any particular interval, you imagine the force is constant on that interval. That's what this is representing, the force on an interval. Multiply by the width of the interval, you get the work on the little interval, you add them all up, you get the total work. So same idea with the Riemann sum. Chop it into pieces, find whatever you're looking for on each interval, add them all up, take the limit, and once again, hand waving, Riemann sum, limit of a Riemann sum gives us definite integral. So if we integrate force, we will get work. And if you look inside that integral, this should have units that match whatever's on the left-hand side. So force times distance will give us units of work. So force is newtons, distance is meters, if we're looking at standard metrics. So newtons times meters is work. So units will be a newton meter, which you could also write as a joule. Either way, newton meter or joule. Or you can do that sort of concept, if you integrate force, you get work. You know, you can think of it in two ways. So let's try it with a spring. So with a spring, when the spring is just laying there, we are going to imagine it at equilibrium, and the origin is usually at the front of the spring, and then you can either compress it, so it's moving in the negative direction, so the force applied is negative, and the distance is negative. So if you go this way, stretching it, force is positive if you're stretching it in the positive direction, and the distance is going to be, your position will end up being positive. So let's try a couple. So once again, for a spring, it's really nice because that force happens to be linear, which is kind of shocking. When you imagine pressing a spring or stretching a spring, feels like it should probably be a more complicated force, you know, but it's just linear, which is kind of cool. So we're going to start with a force of 15 newtons. And it's required to stretch and hold a spring 0.25 meters from equilibrium. Okay, so that's the initial value which allows us to find the spring constant, which is K. K is the spring constant. And it should kind of remind you of college algebra when you did those applications with radioactive decay. Every radioactive isotope has its own decay constant, but you needed some initial value in order to find that particular decay constant. Same idea with the spring. Every spring is unique. It's got its own decay, its own spring constant. So we have to find that constant with some initial value. You have to do some initial test to figure out how to find that spring constant. Okay, so in part A, find K. So we know that Hooke's law says that the force is going to be K times X. So spring constant times the position that the distance traveled. So force is going to be 15 newtons, and it's going to be stretched, so 0.25 meters. It's better to write that as a fraction, so we're going to write that as 1/4. So that tells us that our spring constant is 60. So now we know what the force function is for this spring. So therefore, for this spring, force is equal to 60 times x. So x is the terminal position. So if you're stretching the spring, x is positive and you get a positive force. If x is negative, you're compressing the spring and you get a negative force. Okay, so force will be equal to 60x. So part A is done. Part B says, how much work is required to compress the spring 0.2 from equilibrium? So if we're going to compress 0.2, that means we're starting at a position of 0 on our number line, And if we compress, we're going to end up at negative 0.2, which again, we should probably write it as a fraction, but question, what was that?
Same, flip it. Yeah.
Or it's going to be symmetric. Compressing 0.2 is going to be the same work will be done in compressing or stretching. Work's always going to be positive, but the force could be negative if we compress or positive if we stretch, but it will be symmetric. So in a moment, we'll see why it doesn't matter. So even if it says compress, you could actually write that as like you were stretching it, and you get the same answer. Why? Well, we'll find out in one moment right here. Well, when we integrate this, don't we get a positive always? So we get 30x squared from 0 to negative 0.2. Now we see that, oh yeah, if we went from 0 to positive 0.2, it's not going to matter because that's a square. So the work done whether you compress or stretch will be the same. So this is going to end up being 30 multiplied. Obviously the minus is going to vanish because we square it. 0.2, let's write that as 1/5. So 1/5 squared. And so we'll get 30 over 25, which will reduce to 6 over 5
Joules.
joules. So those, one and a few joules, one and a little bit. 1.2 joules.
It's crazy that 0.05 extra meters of distance is another like 10 times the force to stretch it.
Oh yeah, right.
0.25.
Yeah, so it takes that
Yeah, to pull it.
to go 0.25, and if we're just going to go 0.2, yeah. And it's linear. That's why it seems weird. It feels like it should be exponential or something. Feels like it should be taking more joules. Okay, so let's. I mean, I guess that's a good thing. Like you think about a car, it doesn't have to be that big, that spring, and it can absorb a lot. Okay, and it's just linear. Probably be painful if it was exponential, actually. You know, to try to absorb a big old bounce. All right, so part C says how much additional work. So how much additional work is required to stretch the spring 0.3 if it's already been stretched 0.25 from equilibrium? So this one, it's starting at 0.25, right? It's 0.25 from equilibrium, that's where it's starting. And so if we move the spring in either direction from that point, there's going to be additional work. So what are we doing? Okay, so how much additional work is required to stretch the spring 0.3 if it's already been stretched 0.25? So if we're going to stretch it an additional 0.3, that's going to go up to 0.55. We're going to move it an additional 0.3. Well, we still have the same forcing function. Same force function. Same antiderivative. And again, it's usually better to go into fractions here. So that's going to be 55 over 100, divide everything by 5. So it's 11 over 20. So this will give us 30 multiplied by, square that one, we'll get 121 over 400. Square this one, we get 1 over 16. Plug in your calculator, blah, 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 whatever. You get some sort of fraction at the end that you can figure out.
It's just 25 400ths, right? For 16 times, for 400 divided by 16.
36 fifths.
What was the final one?
36 fifths.
36 fifths, all right. And again, those are joules, units of work. So spring, which you'll do a lot in physics and, you know. So it's kind of, again, these concepts pretty straightforward up to this point. Now we're going to start doing the more interesting, slightly more complex stuff. But this gets us going. So far we just have the basic concept that integrating force is going to give us work. All right, so, oh, one more spring. Then we'll do the more interesting stuff. Okay, so why don't you all try this one? So calculate the work required to stretch the following springs 0.4 meters from equilibrium. Okay, so let me just say something. The first one, part A, is going to be very similar to the one we just did. But the second one, notice that their initial value is not based directly on Hooke's law. They're giving us some sort of initial value that includes work, not just force. So normally, the initial value is going to be force and distance, but here they give us work and distance. So that's going to take a little bit of thinking. So do part A first, and part A should be very similar to what we just did. Part A should be nothing new. Part B, gonna take a little ingenuity. A little ingenuity.
Squared becomes 1 over and then 1 minus 0. I don't know. Did I do it? Oh, okay. I see what you did. So you used 0.1 meters from part A.
Oh.
But
Part A go okay?
that's what I did. Yeah. Thank you.
The part A, very similar to what we just did. So we know that force for a spring is Kx, and they tell us that the force required is 50 newtons to be stretched 0.4 from equilibrium, so we'll write that as fraction, write it as 2/5. And we'll end up with K being, if we divide by 2, we'll get 25. 25 times 5 is 125. So that's the constant for this particular spring. Question?
Is that for part A?
I grabbed the wrong number up there. Thank you. What should that number be?
110.
110. Yeah, I was looking at.
Okay, so you didn't.
I saw the meters up there. The point we haven't. So we have to use the initial value to find K. They want us to find the work eventually of how much work it takes for 0.4, but the initial value is given with a tenth. Thank you.
There we go.
That looks better.
Okay, it's 500.
Now we get 50 times 10, so we get 500. So therefore, the force function for this spring is always going to be 500 times x. So 500x.
You get 200.
And now we can do what the question asked. It said integrate from 0 to 2/5. And we're stretching, so it's positive, and then we put in the 500 times x as our force function. So we'll get 250 times x squared, 0 to 2/5. And that will be 250 multiplied by 4/25. So we'll get 40 joules of work. So that's kind of the classic way that you're given your initial value. It's kind of the traditional way to figure out what the work is. So the second one though is a little bit more, takes a little more ingenuity. So instead of being able to use F equals kx, we have to use this. We have to say, oh, okay, we know that work is equal to this integral from, I'm just going to call it a to b. So they tell us that it takes 2 joules of work to be stretched 0.1 from equilibrium. So that's going to be 0 to 0.1 or 0 to a tenth. And we don't know what k is, so this is what they're giving us. So that's the initial value that they're giving us. They're giving it to us in terms of work and distance instead of force and distance. But that's fine. We can integrate this and solve for k. So this will be kx squared over 2, 0 to 1/10. We can multiply both sides by 2 and get a 4 over here. And then we're going to have k. So I'm just sort of thinking about just leaving this with these two limits of integration. K over 2 is constant. It can be in the front. We can move the 2 to the other side. So now we plug in that 1/10 up into there. So a tenth multiplied by itself will be 100th. And so k is going to end up being 400. And then they wanted to know the work done in going from 0 to 2/5 again, right?
Okay.
So they wanted us to do 0 to 0.4 for both of them. And this one we have a function of 400 times x. So we will get 200x squared, 0 to 2/5. So that will be 200 times 4/25, which will be 32 joules. All right. Any questions on the spring? Now we'll get to the more interesting, kind of deeper thinking. How's it going, Kyle? So let's go to this. So for a spring, force was kx, and you can imagine your spring being this direction or this direction, doesn't really matter. But the bottom line with the spring is that we're not thinking about gravity as being a contributor to that force. Okay, so now what we're going to do is think about including gravity. We're going to think about lifting something or pumping something like water, which is essentially lifting water. And gravity is now going to be a contributing factor to the force. So in general, work is force times distance. But when we're dealing with this vertical motion and it's big enough that gravity matters, with a little spring, gravity just doesn't matter. It's negligible. Force, what's that called? Newton's law. Force is mass times gravity, mass times acceleration. So this is how we're going to think of little pieces of work. Little pieces of work will be m a lot of times they'll put an H in there, mgh. So if you're lifting a block, mass times gravity times the distance traveled, the height that the object travels, the block travels, mgh. So, lifting or pumping, we're going to think of it as the same. And we're going to end up with this formula here. Rho is the density. If usually we're going to be lifting water, pumping water out of the tank. Rho is going to be the density of whatever the fluid is, whether it's water or oil or whatever. So that's density times gravity. Gravity, we're doing the magnitude, so 9.8 typically. So density times gravity times cross-sectional area. We're going to talk about all these things and how to memorize them in a minute. So you don't necessarily have to write everything down right this second. We'll give you a pretty easy way to memorize all this stuff in here. Just tell you what it is for now. So that's cross-sectional area. So if you imagine a tank filled with water, cross-sectional area. Okay? D stands for the distance that cross-sectional area has to travel. And then the dy, you think of taking your cross-sectional area and making it three-dimensional. So the dy is like a thickness. So you've got your cross-sectional area of water, you add a thickness, now you have a slice of water, a little slab of water, a little hockey puck of water. So that's what everything stands for. And the question is, how the hell do you memorize all this? So again, I just sort of point out what everything is here. Mass is density times volume. We already talked about density times volume. So we're just trying to pick things apart, looking at them with units. And if you take area and multiply it by distance, doesn't that give you volume? So that would be density times volume. Or dy is also distance. So you could imagine it being, instead of that distance, you could think that distance. It doesn't matter. The units for d and dy are both meters. So it doesn't matter. The important thing is that, okay, we've got a density times volume, all right? And then we know that force is mass times acceleration. And so then you can combine the others to, there's your gravity right there. Let's see. So force is mass times gravity. So if we have our mass as being density times volume, then this is the only thing left that we multiply by to get force. Force is going to be mass times gravity. So all of this multiplies together to be mass, and then there's gravity. Let's just check the units. So if we look up here, I've got all the units listed out here. When we multiply all those things together, we're going to get the right units. So if we're trying to find work, we are going to end up with Newton meters. Here are all the units exploded out. You'll get Newton meters. Let's try to come up with an easier way to memorize that formula. Trying to memorize that you take density multiplied by gravity, multiplied by area, multiplied by distance, multiplied by dy is a little complicated. We need an acronym in order to write everything down simply. And here is the acronym. The acronym that we are going to use is ADD multiplied by volume. And the way I want you to think about this is that ADD is acceleration, density, depth. Acceleration, density, depth. Acceleration just means gravity. Density is the density of the water, the oil, the whatever. And then depth or distance is how far that has to travel. ADD, acceleration, density, depth. And the volume is the volume of your slice. Volume of slice, which we've already done when we were finding volumes earlier. We would take slices, and you get the volume of a slice by taking the cross-sectional area and multiply it by dy. So this volume, you're thinking the volume of an element of the solid, the element of the fluid. So you're taking the cross-sectional area and multiplying by dy. So that's the volume. That volume in there is a tiny volume. It's not the volume of the whole vessel. It's just the volume of one slice. in a little while we're going to talk about force, we know that work is force times distance. So if we're thinking about this work acronym, if we want to go down to force, we have to take away 1 unit of length. Right? Because work is force times distance. So if we're at work where we have force times distance, and we take away 1 unit of distance, that's going to give us back to force. So the 1 unit of distance I'm taking away is turning volume into area. So we'll talk about that in a little bit. So the book goes through this whole thing, and we come up with this nice acronym, ADD volume. That's pretty easy to remember. ADD is a math word. Volume's a math word, so pretty easy to remember that. And it's going to turn out that ADD actually is going to give us pressure, which also is kind of easy to remember. You feel a lot of pressure, you feel a little ADD. All right, pressure, ADD, pretty easy to memorize. But then they go into the coiling of a rope. And note that the density is one-dimensional density, not three-dimensional density. Let's do a three-dimensional density problem first, because we just talked about sort of all the components to do a 3D problem. Let's do that first. The 1D problem should be easier because it's 1D, but it doesn't sort of give you the kind of the essence of what's happening. So let's go and do a 3D case first, and then we'll do a special case for the 1D. Okay, so we've got a vessel, we've got this tank. Almost time for break. So a cylindrical water tank has a height of 8 meters, a radius of 2. Tank's full of water. How much work is required to pump the water to the level of the top and out? So we're just going to pump it right out of the top. So we're imagining a little valve right up here, and the water's just, ooh, that's not a valve. So we just have a little valve up here, and the water is going to be pumped out this little valve. Okay, so we're finding work, so our acronym is ADD volume. So let's just write that down first. Anytime we're finding work, we're going to go integral ADD volume. So that's our generic formula. Just like the generic formulas that we used before for the area of a shell or the area of a washer, same idea. Generic formula, then we just fill it in. So A is acceleration. Because we're dealing with gravity, that acceleration means magnitude of gravity. So the acceleration that we're using is due to gravity. So there's A. Density, acceleration, density, depth. Density for water is 1,000. It's 1,000 kilograms per cubic meter. Wow, that's simple, 1,000. It's always 1,000 for water. So now we have AD, and now depth or distance traveled by a cross-section of water. So let's come over here and draw a representative cross-section of water. So there's our representative cross-section at a random y. So that y is what it always means, distance from the x-axis. So we've got that cross-section of water sitting up there at y, and we're thinking about pumping that water. So this is the distance that it has to travel, or it's the depth of the slice. You can think of it as either way. And what is that value?
8 minus y.
8 minus y. Is that crystal clear that it's 8 minus y? This y right here is measuring that distance. And if 8 is the full distance, then this partial distance is 8 minus y. All right, so ADD, we've got our acceleration, our density, and then the distance that cross-section travels. Now volume. And by volume, we do not mean the volume of the vessel. We mean the volume of a slice. So we toss in 3 dimensions here. So we say, okay, let's take our cross-section and let's make it into a slice. We're going to add thickness to it, so we're going to put a dy there. So this volume means cross-sectional area multiplied by dy. So that volume includes the dy. So that is going to be, well, every cross-section is the same. Right? It's all 2 meter disks. So area of a disk of 2 meters is pi 2 squared. So for pi, this is the area of the disk, and that's the thickness of the slice. So that right there is the volume. Come on, volume. So this is area. So that's area of cross section. And this is thickness. So that turns your cross section into a slice. And then limits of integration. Limits of integration always represent the physical location of the fluid. So that water is from y equals 0 to y equals 8. So we'll integrate from 0 to 8. Now if we go through and check all the units here, these units are all going to give us Newton meters. So if we include the unit for the differential, this is all going to give us units of work in there. But that's a pretty simple way to put everything in its place. ADD volume. And by volume, volume of slice, not volume of tank.
Almost all of it comes out.
And almost all of it comes out, right? There's only one little linear term that's in there, linear factor. So we're going to have 9,800 times 4 pi. Integral is 0 to 8 of 8 minus y dy. That's it. Once you get the setup, the mechanics of these integrals is pretty easy.
It'd be more difficult if you had a variable.
So if we have a cross-sectional area that's variable, like if we have a cone or a trough, it's going to add one extra level of complexity. So then we're going to have 8y minus y squared over 2.
And if you're pumping the water high enough, the gravity becomes more.
So this is another question. What about, let's suppose we put a pipe at the top, and instead of just having the water flow out at top level, what if we wanted it to go 3 meters higher? Trying to pump it 3 meters higher. What would change if instead of pumping it right out the top, we did this and pumped it out 3 meters taller?
Well, wouldn't we just add,
12 minus y.
11 minus 1.
Sorry, 11 minus y.
Well,
yeah.
that's the only change.
You'd have to change.
Limits of integration stay 0 to 8 because the limits of integration represent the physical location of that water. And if we just add a pipe to the top, that's not changing the physical location of the water, but it is changing the distance traveled. Right? The distance traveled, we would end up with an 11 minus y right there because this full distance is now 11 and this distance is still y, and so that partial distance would be 11 minus y.
But it also has
does
to
the
take
area
account
of the
for
cross
that.
section change though?
Nope. We still have so again, we're looking at the physical location of the water. That physical cross section of water still is not changing. That makes sense?
Diameter of the pipe though?
It's not going to matter.
No?
I mean, it's got to be big enough to get, that's all going to depend on how, that's going to tell us how fast it will take.
And also like friction and stuff if we have.
And there could be some extra, extenuating variables that we always ignore.
Ignoring friction.
Ignoring friction,
The width of the pipe doesn't matter.
right? Ignore friction.
Always.
Always ignore friction for now. Yeah.
Is the answer like to the original problem like over 1 million?
I don't know, let's find out. So we plug in 0, get nothing, so all we have to do is plug in the 8. Let's see if we plug in the 8, what we get. I'll pause and not multiply that out yet. So that's going to be 64 minus 32, so that's 32. And so then we just have to multiply these things together. 9,800 times, let's see, 32 times 4 is 128. So whatever that is, joules, what's 9,800 times $1.28?
So 1,254,400.
Perfect.
That sounds like a big answer, 'cause I was like, what's the answer? I was like,
It's a lot of joules.
It takes a lot of time. It's also a lot of water if you think about it. Like a radius
Yeah,
2 meters by 8 meters.
that's enough for me to go, that's enough to like go swimming in.
Yeah,
Yeah,
Almost.
basically.
yeah. Swimming
Well,
down.
4 meters
That's
across.
where, yeah.
I mean, 4 meters across is still like
12 feet.
more than a hot tub usually.
Yeah,
right?
yeah.
It's like-
Definitely more than a hot tub.
Like
More,
Yes, it's-
more than my hot tub,
it's like-
because I don't have one.
It's like a
It's like
water
a mini
tower.
pool.
Yeah.
All right, let's take our 10-minute break. 10-minute break. Then we can find more
Wait,
jewels.
that's a mini deep end pool.
Yeah, so 4 meters, 13 feet across.
That's like a really, like a small deep end pool.
But 8 meters deep that's pretty deep. You don't see a lot of pools that are 8 meters deep.
Most deep end
Wait.
pools
4-ish feet deep.
On
are
7.6,
like
Yeah.
3
you
meters.
said somehow from even megasecond times 0, you got
So that's so 0 times the whatever that number is 0.
0.7 mass.
So was that in this one? Or
It was under 6.7.
oh, what was 6.7? It was 6.7 right there. So so -2 times 0 is 0,
Right.
and
Which
e
is
to the
1.
0 is 1.
Yeah. How'd you get -8?
Because if we plug in a 4, we get 4 times -2,
Oh.
which is -8. So we have e to the -8 when we plug in the upper limit, and we have e to the 0 when we plug in the lower limit. And then the e to the 0 becomes a 1, and we're subtracting.
Okay. Yeah. That makes, cool.
Mhm. Do some more? Some more pumping? Let's see, so we did the cylinder. Let's go ahead and do the other 2 kind of classic tanks. Let's do the trough first, and then we'll do the cone. Cylinder is obviously the easiest. Like you pointed out, cross-sectional areas were all constant, and if the cross-sectional areas are variable, it's going to add complexity. So same concept here. We've got a trough. It's got a semicircular front, radius of 1/4 meter, and the length of the trough is 3 meters. How much work is required to pump the water out of the trough, just out the top? So first off, let's think about, well, let's write down our acronym first. So the work is going to be the integral of ADD times volume. ADD volume. And let's start filling in the blanks. We'll fill in the ones we know right away. So acceleration, density, depth. Acceleration, density, depth.
9
Acceleration of density is 1,000. All right, depth. Let's think about that for a moment. I'm going to draw a cross-sectional element or cross-section of water, however you want to think of it. So I'm going to think about this, I'll call it W across the front. And isn't a cross-section of water, isn't it going to be a rectangle? It's going to go all the way back, come across the back, and then all the way down the side here. So a cross-section is going to be a rectangle. And if we say that this cross-section is at a height of y, we're going to think about the graph of the face as a semicircle. I'm going to draw it literally how it looks, so it's on the ground. And that cross-section that I've drawn right there, that representative is right there. That's going to be the W across. And if it's at a height of y, what is going to be the second D?
0.25 minus 1.
0.25 minus y. Everyone agree with that? So 0.25, I'll write it as 1/4 minus y. So that's the depth of that representative element. It's the distance traveled by that cross-section. So that's ADD. And everybody's comfortable with that? So if this is y here, then this is 0.25 minus y. That's messy. Write it as a 4th minus y. Okay, all right, so there's our ADD. Now we have to multiply by volume. And by volume, We mean the volume of a slice, not the volume of the trough, volume of a slice. So the volume of a slice is going to be that cross-sectional area multiplied by dy. So that cross-sectional area is 3w times dy. 3w times dy. So this is volume of slice.
And what's W?
W is the width across right there. Width across, which we have to figure out. So now we're adding thickness to this, right? We're thinking of it as now as a slice and not just a cross section. Cross section is two-dimensional, has area. Multiplied by dy, we've just added thickness to it. We've made it from a cross section into a slice. And now the million-dollar question is, how do we find W?
Pythagoras.
Yeah, we wish. We wish it was that simple.
Did you use Pythagoras with?
I'm
'cause you know
calculus.
Times 2.
you know the hypotenuse and you know the height.
Wait, I don't see a triangle.
The radius of this semicircle.
Radius of the semicircle, but the
is-
radius of the semicircle is variable.
Well, no, the radius of the semicircle is always 0.25. So that's the hypotenuse.
But if we take a horizontal cross section, we're finding horizontal distance. We have to find this distance right here. And that's not a radius anymore.
Well, but you can use the radius and the depth of the water as a triangle to find half of the W, correct?
Me, I don't
Probably
know.
an easier way than
I
this.
would like to see that way work. The normal way that we've talked about, if we're finding horizontal distance, do we want x's or y's?
Wise would work. I don't think.
Horizontal distance, we want x's, right? Horizontal is always x's, vertical is y's. So we are trying to find the distance. If we want w, we're trying to find the distance across this semicircle. That's a horizontal distance. Horizontal distances, we take the right x value, subtract off the left x value. All right, so we're just back to what we did last chapter. Horizontal, right minus left. So we need to write, this is the curve that's bounding that horizontal w, and this is bounding it. So we need to write each of those as x's. So we have to come up with the equation of that circle and then isolate x. All right? So the equation of this circle, this point right here is the center of the circle, which is at 0, 1/4, because it's a circle of radius 1/4. So the equation for this circle is x minus 0 quantity squared plus y minus 1/4 quantity squared equals 1/4 squared, radius squared. So that's the equation of that circle. And we want to isolate x. So if we isolate x, we're going to have x squared equals 1/16 minus all these y's. Let's multiply it out. That's going to be y squared. The middle term, minus 1/4 y times 2, so that's minus 1/2 y. Plus 1/4 squared is plus a 16. 6. So we have that. And then we take the square root to isolate x. There's going to be two options, of course. So x will be plus or minus. Notice that the 1/16ths cancel. This minus distributes and makes that a negative 1/16. So we're going to end up with plus or minus the square root of, looks like negative y to the 2 plus 1/2 times y. So now we have the left and right half. The right half over here, the right half over here is going to be the positive square root. Come on. So annoying. So this is going to be x equals the positive square root of negative y squared plus 1/2 y. Okay, so that is measuring the distance from the y-axis over there.
Every time you do it, it's a hard.
I know, why? That's a strange. I have no idea why.
It's because Valentine's coming up.
No, it isn't.
No.
It can't be. If it's that simple. All right, so
So we
Now-
multiply by 2, right?
we could just double it.
Yeah.
We could just double it. So does everybody see that if we double that, we'll get the whole chord all the way across? If you wanted to be super technical, you could write the left-hand side as the -1, and then right minus left, you'd have square root minus minus square root, which is twice the square root. So W, so this is going to tell us that W is twice the square root of this. There's W. All right, now,
We have 2 W's now. No, forces were as being represented by W.
No.
Or work.
W with the, this is baby W.
Yeah, baby W.
Baby W. Baby W, not work W. Not granddad W. All right, so then limits of integration, we said were 0 to a quarter. Somebody said that at one point. So 0 to, let's pull out some constants. So 0 to a quarter. Certainly the 9800 can come out, and so can the 3.
It's okay, the 2.
And the 2 also can come out. If we can do it all at once, let's do it. So 9800. That 3 is coming out. In the W, there's a 2, so we're going to bring out a 6. And so let's see what's left. So we have the 1/4 minus W from there,
1/4 minus y.
and then that. 1/4 minus Y. 1/4 minus Y. And then the W, we already pulled out the 2, so then we have the square root of negative y squared plus 1/2 times y dy. So that's where we're at. Looks pretty gnarly. Not gonna lie, it's gonna be pretty gnarly. So, let's just leave the 9800 times 6. Maybe there'll be something that's gonna cancel. When we take if this was gonna integrate in the simplest way possible, we see a square root, we let u be what's in the root. That's the dream. That's what we're hoping will work. Let's take a look at the derivative of the inside here and see if the derivative is present on the outside. Let's just check. So everybody agree with that derivative?
Or that's supposed to be a plus?
It's,
Or is
it's close.
negative y? Because of y, negative y squared.
That is supposed to be a plus, thank you.
Okay.
So I want to move, let's just move that. Where is the escape button? Okay, there's the escape button. I just want to move this thing maybe a little more this way. So let's divide, we see that that's got a negative y right there. So let's divide both sides by -2 to see if we can match it exactly, or by +2. So if we multiply both sides by 1/2, we'll get du over 2, and this will be -y. Oh gosh, that becomes +1/4. So that matches. So it does match. If we divide out a 2, then we get this part right here, 1/4 minus y, that's 1/4 minus y, times dy. So we now have a match between the outside of the root and that differential. So substitution is going to work.
We're dreaming.
Lucky us.
Yeah.
Lucky us. Okay, so we're letting u be what's in the root. So that's going to be square root of u. And then 1/4 minus y times dy, 1/4 minus y times dy is du divided by 2. And we'll put that division by 2 out in the front. So we have that. And then we want to convert our limits of integration. If we plug in y equals 0 here, plug in y equals 0, we're going to get a u equals 0. And then if we plug in a y equals 1/4 into this, we're going to get negative 1/16 plus 1/8.
So
An eighth minus a 16th is a 16th. 2/16 is an eighth. So I forgot what I just said. So if I plug in a quarter, it's minus a 16th plus an eighth, which is a 16th. Okay, so 16th goes up there. So then this gives us 9,800 multiplied by 3, just waiting to the end. So this is going to be a u to the 3/2 when we integrate, divided by 3/2, multiplied by 2/3, 0 into 1/16. So the 3's are going to go away. So we're going to multiply those two together. We get 19,600.
The threes cancel.
3's cancel.
Yeah, that's what 2 times that.
And then, let's see, 16th to the 3/2. Trigger the denominator of that exponent first. So the square root of 1/16 is a 4th. And then a 4th cubed is 4 times 4 times 4, which is 64. So 1/64. Minus 0, so we don't need that. And then we just divide those two. And someone have that as a fraction?
Get you to 1,225.
Say that one more time.
1,225. If I did my math correctly.
That seems
I got 1,225 divided by 4.
divided by 4.
Divided by 4, did I miss something? Oh, that was a 16, sorry, my bad.
Yeah, okay.
Not 16.
And what were our units? This was work, right? Can't even remember anymore. So joules. So that's a hard one. The trough is always hard if anytime there's a semicircle, you've got to deal with that right and left business, which, adds complexity. All right, let's do a cone. Cone will be in between. Not as easy as the cylinder, but not as hard as a trough. So, again, acronym, we know that work, big W, is the integral. Why are you thinking I'm a mouse? So, ADD volume. And let's start filling in the blanks. So again, acceleration due to gravity. Again, density of water is 1,000. Let's draw a representative cross-section. So cross-section is a disk. We're going to think of it as the cross-section at a height of y. So this direction, that's y right there. So exactly, so 6 meters is the total height, so 6 minus y. That'll be the distance traveled by that cross-sectional piece of water. So ADD, and now volume. Volume means the volume of the slice. So now we add thickness to that slice, which is just dy. So we need cross-sectional area multiplied by dy. That's it. All right. Well, in order to find the area, we need to know that radius. And we want everything to be y's. We're integrating with respect to y, so we need to somehow come up with that radial value as a function of y. So let's see. Well, if we did this, let's just take out this right-hand diagonal line there. And this distance right here is 1.5. And we're trying to find this radius right here. And this height is 6 over here. So, any ideas?
Equation Hypotenuse.
So we could, and we're going to think of this as y right here. So we could set up a proportion. We could use Pythagorean theorem. There's a whole bunch of ways we could get at this. We could pick points. You know, if we wanted to think about finding the equation of that line and solving for which letter? X. Because we're trying to find horizontal. Could do that. Lots of ways that you could get at this. The simplest way is probably just to find the equation of this line and then solve for x. And that's a super easy line to find the equation of because the y-intercept is 0. So it's really just y equals mx. Right? Slope of a line through the origin is mx. And slope is rise over run. So the rise, if we go from this point to this point, the rise is 6, the run is 1.5, rise over run times x. So that goes in 4 times. So that equation is 4x. And if you isolate the x, you get y divided by 4. So that's the radius as a function of y. So that tells us what the radius is at different y values. If y is 0, we're at the bottom, radius is 0. If we're at the top, the y value is 6. Plug in 6, you get 3/2. That's the radius. So that's probably the easiest way is just to find the equation of the line and solve for x. Very similar to the semicircle, find the equation of the semicircle, solve for x. But a little harder to solve for x there. So now we can just plug in, let's use a different color for the volume. So the volume is going to be pi r squared times dy. And r is y over 4. So pi r squared dy. So there's the volume in blue. So the biggest mistake is sort of finding the volume of the whole cone. By volume, we mean volume of a slice. So area multiplied by thickness. And then our limits of integration, tank is 6 meters tall, so 0 to 6. Again, most of it can come out. We're going to get a 9800. That's going to look really familiar. So 9800. A pi can come out. And a division by 16 can come out. So let's see, we're left with 6 minus y multiplied by y squared. How's that look?
Solvable.
Solvable, right? That's just going to be a polynomial, so it's not going to be too hard. So I'm just going to leave these constants for the moment. Maybe something will cancel. So this is going to be the integral of 6y squared minus y cubed dy, 0 to 6. So 9800 pi over 16, integrate. Add 1, divide, so we get 2y cubed minus y to the 4 over 4. 0 to 6. 0 gives nothing. Plug in 6, we get 6 cubed, which is 216, times 2 is 432, minus, whatever that's going to be. Oh, you know what? I'm going to leave it this way. I see, we're going to have a common factor of 216. So let's leave this as 2 times 216 minus 6 times 216 divided by 4. Right, 3 6's multiplied together is 216, so if we leave one out, then we can pull out the 216. It might be a little faster. So times 216 times, what are we left with in here? 2 minus 3/2, which is 1/2. So it's going to be 9800 pi, that's a half, divide that into there, we get 108, divided by 16. and 80, let's see,
66,155.
thank you. Someone concur, 66,150?
Yep.
Yeah.
All right, cool. And these are units of work, so joules. Joules. So those are the three types of vessels that we're going to see: troughs, cylinders, and cones.
What about like trapezoids or hexagons or squares?
We'll have trapezoids that are, well, we can have a trough that has a semicircle or a trough that has a trapezoid.
They just gotta be symmetrical.
Has to be symmetric, yep. Let's go to the chain now. So now we've done this enough. So it's a lifting problem, which is similar to pumping. The big difference is that this is 1D instead of 3D. So normally our acronym is ADD volume, but because we're taking away 2 dimensions of this density, instead of a volume here, we just have length. And that, whatever's in that parentheses, whether it's ADD volume, ADD area, ADD length, the differential is always part of that parenthetical chunk. So this is just dy. It's just dy. For a rope or a chain, it's always just dy. Because like we just had, we found that volume was cross-sectional area times the thickness, which is dy. Well, you can think of that cross-sectional disk as just shrinking down to a point, and we just have the thickness now. We don't have any cross-sectional area.
Do we have to convert the density to kilograms per meter?
Yes. So we do have a unit issue. We want to have everything in kilograms and meters. And so we will have to deal with that thing right there. Okay, so let's try to fill in the blanks then. So the work is going to be A, that's still the same. Density is 55 grams per meter. So if we want to change that, we're going to have 1,000 grams per kilogram. So we could write it that way, so we're going to divide by 1,000, so move it 3 to the left. So there's ADD. Let's draw a picture. So we've got this scenario where the rope is hanging freely from a ledge. So it's hanging down like that. It's 60 meters long. So this is going to be the ground down there. That's 60 meters. If we take a cross section of rope, that's just, you can think of it as a point of rope. That's going to be, we're going to say it's at height y. So the distance that that little piece of rope is going to travel is 60 minus y. So there's our ADD, and then length. Length when we're dealing with a rope or a chain is just the dy, because there's no cross-sectional area. And we're going to lift the whole rope up, so this is going to go from 0 to 60.
So 60 minus y is dy.
60 minus y is the distance that that piece of rope travels. So 60 minus y is going to represent this distance. So all the pieces, this piece down here is going to travel 60. That piece will travel 0. The one in the middle is going to travel 30. So this is going to add up all of those cumulative little works, and each of the little works is going to be based on a different distance. So we'll get all the distances traveled by all the pieces of rope. And that will give us whatever we have when we multiply this stuff together. So
Obviously the width of the rope compared to the height is so small.
negligible, yeah.
It's all encompassed in that dy.
Yeah, exactly. So we're thinking about just that. And I think a good image is when we do the cross-section of the cylindrical tank, it's got a radius. And so we have a cross-sectional area, but that thing is being shrunk down so small that we just don't think about it as having a cross-sectional area.
Also here, the cross-sectional area is encompassed in density being per length.
Unit.
per unit length instead of per unit volume, because you're already dividing out by the
2 dimensions.
2 dimensions to get to that.
You're shrinking 2 down to 1. And when we do this integration, the integral of 60 is 60y, and the integral of y is y squared divided by 2, from 0 to 60. So whatever this all multiplies out to, plug in 60 there, and we get, what, 36, so 3,600 minus 1,800, so 1,800? So whatever that multiplies to.
So the diameter of the rope doesn't matter?
Correct.
Okay.
Hey, good point, because they give us the diameter of the rope.
Yeah.
So if we have a 9.4 millimeter climbing rope, the diameter does not matter. Correct. Correct. Yeah, so they they did one of those, SAT type things where they give you too much information.
But it would have mattered if it were in grams per meters squared.
Correct. Yeah, so if this was given to us in grams per meters cubed, then we would definitely need to find the radius of that, divide the diameter by 2. Then we would have to do the same thing we did for the cylinder. Yeah. Correct, correct. Did we get a number for this?
4851 divided by 5.
4851 divided by 5? Thank you.
Then why is it 1,800?
36, if you put 60 in here, you get 3,600.
Oh, because it's not.
And then this is 3,600 divided by 2, which is 1,800.
Okay.
All right, let's do one more of these ones. So here, we've got a 30-meter chain hanging vertically from a cylinder. So we've got some sort of cylinder, and then we've got our rope, 30 meters. And it's going to be winched up. So here, again, they give us density as a one-dimensional density, kilogram per meter. So our acronym will be work equals integral of ADD length. So we've squeezed out 2 dimensions, we just have length, which will always be dy. So we're going to have our 9.8, and then the density is 5. So AD, let's see, D. So this is a piece of rope at a height of y. We imagine the ground right there. So 30 minus y. That will be the distance traveled by that piece of rope. And then length is just dy. Don't have to do anything funky. No right minus left, nothing weird. And this will go 0 to 30. We want all pieces of rope. And integrate that. I think we've done enough of those. 30y minus y squared over 2. Plug in the 0, plug in the 30. So that's not too bad. Now, second part is a little more interesting. So the second part, how much work is required to wind the chain onto the cylinder if a 50-pound block is added to the end of the chain? So if we put a block down here at the end of the chain, then it's 50 kgs. We can think of it in 2 parts. We have to wind up the chain, and we have to lift the block. So the only difference in B is that you're still going to have the work up here. So we still have all that stuff from up here, all that. But then we have to lift the block, and the block is just found by doing MGH, mass times gravity times height. So the mass is 50. Gravity is 9.8, mg, and then h is 30. So mass times gravity times height, or distance traveled.
Because it is going in a vertical direction, yeah.
This is going directly vertical, so we're using gravity, we're pushing against gravity. So we still do the integral part for the variable distance traveled, but then this mass is constant, gravity is constant, and that's just lifting the block. It's like a point mast. So here is a super interesting slide, if I do say so myself. So this is interesting because, so here's the idea. So we have a 40-meter chain. I've made it into a couple of different segments because, and density I just picked to be 1. How much work is to wind it up? Halfway. So here's how I think of it as a math person. Say, okay, so the orange piece is the part that's going to be wound up, right? It's the links between 20 and 40 that are being wound up. And the bottom is acting like a block. This is acting like a block. This is what the terminal, what it would look like once half of it is wound up. So you could think of it like this. You could think of the orange links and then the block, and when it's wound up, you just have the block at the top. So if you think of it this way, the links that are moving are the ones between 20 and 40. So you're integrating from 20 to 40, and then you're lifting the bottom piece of the chain as a separate block like we just did. That's how I did it. Well then, I don't know, some years ago, I had there's always some physics people in here. I'm like, well, why don't we just integrate from 0 to 20? So there are two perspectives. I would call this perspective up here the reality method. We are doing what physically is happening. We are moving the links from 20 to 40 up to the winch, right? And the bottom is just hanging there like a block. That's the reality method. Here is another way that will work, and you can test it and see that you get the same answer. So I'm calling this the initial state versus the terminal state. And the perspective here is that let's imagine the terminal state is that 20 meters of it is hanging. So let's just imagine moving this chunk of chain, the bottom 20, up to the top. So we're going to integrate from 0 to 20 ADD length, and those are just it's going to be like, like quantum leap. They're going to leap up to the top. This will give us the exact same answer. So you can think of it that way, where the terminal state, there's 20 links up here. Well, you can imagine them being these 20 links getting up to there. And the distance that they would travel, you're going to integrate from 0 to 20, and now you're imagining your y here, and the distance that link travels is still, right, that's going to be 40 minus y that it travels. And if you work out both integrals, you will end up with the same answer. So, but in physics books, they tend to just do this, which I didn't understand at first, because this is how I would have set it up, being, a math person, step by step, not thinking outside the box. That's the reality method. But that's a cool method. It will work. Okay, so we did cylinder, trough, and cone. Let's go to pressure. Pressure. So this gets at that concept we talked at the end of class last time, that when you look at a dam, it doesn't matter how much water is behind the dam. All that matters is that film of water that's on the dam that matters. That's what determines the force. So, and that's the whole concept behind hydrostatic pressure. Hydrostatic pressure, a little particle of water is pushing in all directions equally, simultaneously, all directions. So when you're standing at the bottom of the pool, you're feeling pressure from every place, so you're feeling it everywhere, right? From the bottom of your feet, top of your head, everything is coming in. So the only thing that's going to be really different, let's go here and look at that picture right there. Oh, there it is. Okay. So we're going to imagine that as being either a window in a pool or a dam, however you want to imagine, water is pressing against it. And so the Riemann sum idea is that we are going to, so if you take a strip across, a horizontal strip, you have constant pressure at any horizontal level, right? If you go 10 meters down in the pool, the pressure across is the same. If you only go 2 meters down, the pressure across is the same. So at any horizontal spot, the pressure here and the pressure here and the pressure here and the pressure, those are all the same. So we can imagine on a particular strip there being constant pressure. And so then we want to add up the force at each of those strips. There's going to be a force that we are going to accumulate that's against the whole wall of the dam. So that's going to be the idea. So force is going to be pressure times area. Pressure is the ADD we've been doing. ADD is pressure. Acceleration is gravity. The first D in our ADD is density of water, if it's a regular water pushing against a wall or a dam. And then distance, which means depth. Okay, so same ADD that we just did when we were finding work. The only difference is that instead of out here at the end where we had volume, now we just have area. And by area, we mean the area of the strip, not the area of the whole face of the dam, just the area of the strip. Just like when we found volume, we meant just the volume of a slice, not the volume of the whole vessel, just the volume of a slice. And we're in 2 dimensions now, not 3. Right? We're just dealing with the face of the dam. We don't have 3 dimensions. We don't care about all the water behind it. We just care about the face of the dam and that film of water on the dam. So we're in 2 dimensions. So we should have area instead of volume. Area across. All right, and the units are all there. You can look at them carefully and make sure they all line up. Let's try one. So again, we're going with our acronym. Force is 1 dimension down from work. Work is force times distance, so we're chopping off 1 distance. And the 1 distance that we're going to chop off, we're going to leave the ADD alone, that's pressure. And instead of volume, we just have area. We're taking away 1 dimension, 1-dimensional length. And again, when we talk about area, we mean area of strip. And the strip, we draw a representative element across right there. So that's 1-dimensional, but then we make it a strip by adding some thickness to it. Now it's 2 dimensions. We mean the area of that. The thickness of it is dy, and then we'll call the width of it w, little w. So this whole thing is going to be w times dy. So let's, acceleration, 9.8. Density, 1,000. It's water pushing against this. So we've got a dam with this wall, so water's pushing it. So same as the other ones, AD. And this D is also the same. So if we say that this is the strip at Y, instead of thinking distance, you can think of depth. Doesn't matter, it's the same thing. So the depth below the surface is
15 minus Y.
15 minus Y. So really it is parallel to what we have just been doing.
And is the water pushing from the right or
It's pushing against the face here.
pushing it on the face of that? So that's the shape of the, if we're looking at it, if you look at it from the front.
Yeah, if you're underwater, you'd be seeing the big trapezoid.
Okay.
Yep. So that's the depth. So at this depth, you have constant pressure. There is the pressure at that depth. And if we multiply by the area of the strip, we will get the force at that depth. So now we've got to find W. All right. This is like the cone problem. If you imagine an axis in here, if you imagine a coordinate system like this, really what we could do is find the equation of this line right here, and then we could solve it for x and double it. So let's go with that method. So this point right here, if I did use that coordinate system, this would be 5, 0. And this point up here would be 10, 15. Exactly. So 15 is the height, so that's the y value. And 10, this trapezoid is symmetric, so half of the 20 is the 10. So now we have 2 points on a line. We're going to use the point slope formula to find the equation of the line. So we're gonna do, and we'll pick that point. So y minus 0 equals the slope. Slope is the rise, which is 15 minus 0, over the run, which is 10 minus 5. Y is minus, subtract the y's, subtract the x's, times y, oh, I put the 0 in the run, oh no, no, that's an x. X minus 5. So point slope formula, y minus y1 equals slope times x minus x1. You can pick either point. You could put the 10 here and the 15 here if you want, it doesn't matter, any point. But I will always pick the point that has a 0, just because it's less work. But you can pick any point that you know on that line. So this gives us y equals 15 over 5 is 3, so you get 3x minus 15. Solve for x. So we're going to add 15 to the y and then divide by 3. So there is half the distance across that trapezoid.
Then double it.
And then we'll double it to get the full W. So W will be, the little w will be 2x. So that's going to be 2 times y plus 15 divided by 3. Yeah, so that'll be all the way across. So that is the width of our strip. Width of that strip. The area of that strip is the width of the strip multiplied by dy. So now we're going to take the width of our strip. So 2, let's write it as 2/3 and y plus 15. 2/3, y plus 15, and then dy. So this right there is the area of the strip.
Move all the constants out.
All the constants out, and then we have a little polynomial to integrate. What about limits of integration? 0 to 15. There's water on the entire face of this, so from 0 to 15. Pull out all the constants, so it looks like we're going to have a 9800, once again. Looks like a 2/3. And then 0 to 15. And then the only stuff remaining, we've got this factor right there, and we have this factor right there. That's all that's left. Let's FOIL it out. So we're going to end up with negative y squared minus 15y plus 15y. Those cancel, and then plus 225 dy. And once again, the integration there is, typical stuff we've gotten very good at. So negative y cubed over 3 plus 225y, 0 to 15. Plug in the 15, collect everything together, turn it into a fraction. And we are finding force, cumulative force on that wall, so we should have units of newtons. Force is in newtons, work is in joules.
And newtons is in kilometers.
Newtons, yeah. No, newtons is meters for length and kilograms for mass. So yeah, kilograms and meters.
Again, I got a really big number.
Yeah, me too.
I got 1.4 times 10 to the 7. Sorry, 1.47 times 10 to the 7.
No, 14,700,000.
Yep.
Just sign notation.
Sorry, I don't
1.4.
want to write that many zeros.
Yeah, exactly. Scientific notation is fine.
A lot of force.
All right, a lot of force. A lot of force. All right, let's do one where we use a triangle. So now, just like the different types of troughs or whatever, different types of containers. Now we're gonna have the same type of thing, different types of faces. And they basically are paralleling what we did with the other ones. It's just 2 dimensions now. All right, so there we go. Once again, we want to do force is equal to ADD area. Oh, I didn't put my integral there. I mean, it's true that this is true. This just means if I don't have the integral there, we're just thinking of a little force, you know, like one cross section. But when we find our total force, our cumulative force, we're thinking of integrating ADD area. So we're going to integrate ADD area.
And we assume this is also water.
Water again, yeah. Yeah,
Water on the surface.
they preface it, it's always water for this book.
We're not doing the nitrogen ban on space.
And no beer, no oil, nothing interesting, just water. Mathematically, water is nice because it's just 1,000. Keep it simple. Yeah, right?
It's not,
Certainly wasn't in the...
Nice definition of a kilogram.
it wouldn't really be that much, it wouldn't really make the calculus any harder if it was different, but.
Right, it's just, it makes that multiplication a little bit different. Definitely easier to be in the metric system. The numbers actually have a meaning. Okay, so acceleration, density, what do we think for depth?
30 minus
30 minus y. So this is just a representative little cross section across the dam or across the window, whatever we think of it as. So the distance below the surface is 30 minus y. So that's what dictates the pressure. Right? Constant pressure at a particular depth. So 30 minus y. So that's pressure. All that's pressure right there. This all is pressure. ADD. Does it make sense? So when we're at a height of 30, we're at the top, we have 0 pressure. Put in 30, we have 0 pressure. If you're at the bottom, y is 0. Plug in 0, you have max pressure. Okay? And then once again, by area, we mean area of that tiny little rectangle here. We imagine this as having some thickness. And so that's just W times dy. W times dy. That is the area of the strip. Okay, so let's come over and find the equation of this line. This is going to be y equals mx. Because we're imagining a coordinate system right here, and we're imagining this coordinate system, and we're trying to find the equation of this diagonal line through the origin. And if that line's going through the origin, the y-intercept is 0, so it's just mx. M is rise over run,
30 over 10.
so 3x. So if we want to think about points, this point right here is 10, comma 30. This point is 0, comma 0. So rise is 30, run is 10, so 30 over 10 is 3. Isolate the x. So x will be y divided by 3. So what does that make w? 2y over 3? So that's 0 to 30. So this tells us W will be twice that. X goes halfway across.
Yep.
Double it to get all the way across. So we are going to have 9,800 out in front. Let's pull out the 2/3 too. Let's pull it out now. Let's not wait. I think you see that it's coming out. So that 2/3 is coming out, and the stuff that's left, we have the 30 minus y multiplied by y. So that'll be our integral. Any questions on where any of those pieces came from? When you just look in the book and you see some of those formulas, it can feel really overwhelming. But if you just break it down to a simple acronym, which is a really good way to do physics, is to look at the units and build an acronym based on the units. That's a great way to go. Because if you've got the units right, the chances that you have the wrong formula are pretty unlikely. You can match all the units. Okay, so we're going to have 9,800 times 2/3. This is 30y. When we integrate 30y, we get 15y squared. And minus y squared, when we integrate minus y squared, we get minus y cubed over 3. And that will go 0 to 30.
And
Yep.
this one, if you keep the first part as 30y squared over 2, don't you end up with a common factor of y cubed for both of them? Or 30 cubed? Because it's 30 times y squared, which is 30 squared.
It's 30y.
So if you keep it as 30y squared over 2 instead of actually using the division for 2, you end up with a
Going
common
down to
factor.
here?
Yeah. And then you just have a multiple.
Oh, yeah. I got you. Yes, that's a good point.
Because then
Yeah, if you left this as a 30, yeah, totally.
So as long as you're integrating from the top to the bottom, if you leave it always as the 30s, things will.
Then you can
cancel out.
then you can factor out that, absolutely, factor out that y cubed.
It works no matter what.
Yep, that will work out absolutely perfectly. And when we plug in 30 here, 30 times 30 is what, 900? So 15 times 900 minus,
27.
yeah. You do that. However you want to combine all those numbers.
Oh, I see what you're saying.
You could.
The 30, yeah.
Yeah, pull a 30 cubed all the way.
So then you'd have a 30 there and a 2 in the bottom.
Yep.
And then you can factor it out. Yeah, that's a clever way to
30
go.
cubed all the way.
The 15 and the
So what do we end up with when you type that all in?
1.94 times 10 to the 7th.
Perfect, thank you. And these are newtons, not joules. All right, any part of that? All right, so let's take a look at this last slide. We will never get all the way through it, but let's talk about it. As soon as you see a circle or a semicircle, it just, you just have to, hesitate, because as soon as you see a circle, you need to deal with getting across a circle. And anytime we get across a circle, horizontally across, we need to get the equation of the circle. So context here, we've got a pool with a circular window down here. Radius is 1/2 of a meter. Depth of the pool is 4 meters. So that is the equation of that circle. The center of the circle is at 0, 1/2. So it's x minus 0, y minus 1/2, square them both, equals the radius squared. And if we're going horizontal, we have to solve for x, so we move the y's over, solve for x. So this is going to be 1/2. That's going to measure from the center, that axis, over to there. That's what that x is representing. Measuring to the right from the axis, the vertical axis. And then we'll just talk about it. We'll do this one in detail on Thursday. Again, force is pressure times area. Pressure is just ADD. ADD is acceleration, density, and depth. And then area is the width times dy, and
Squared, double, yeah.
that's doubled.
Yep.
Yeah. So we'll talk about it on Thursday, but just look at it. Maybe try to work it out.
Thanks.
All right, let's take a break. Take a big break.
More calculus?
More calculus. It never ends.
Take your break.
Never ends. The world of life is calculus.
But we have calculus homework too,
Calculus for
so.
16-week classes.